Continuity. One way to look at continuity is to say that a function is continuous if the graph has no breaks or holes. If you can draw the graph of the function without having to lift up your pen or pencil. So what could cause there to be a break or a discontinuity in a function? If we look at a graph of a function that's not continuous, it can be a little more interesting. So here we have a function which is certainly not continuous. There are several breaks in this function. Let's look at each one here and see what's going on with the function. This first one here at x equals 1, we see that there's a hole there, so the function is undefined. If this is the function f of x, then f of 1 would be undefined. And that certainly would cause f to not be continuous at x equals 1 right here. If the function is not defined, then we have a missing point or a hole here, and the function can't be continuous there. At x equals 2, we have a vertical asymptote, and so we see again with this asymptote that the function is undefined here, is approaching infinity, and therefore there is a discontinuity here. There's no value for the function. It has to skip 2. Now, looking at x equals 3, the function is defined here, but there's definitely a break in the function. So just because the function's defined, that doesn't guarantee that we're going to be continuous. So what's going on here with this one? Well, if you look on the left side, the function is approaching this point up here, where the function value is, but on the right side, the function is approaching a y value that's down here that's different. So this left side and the right side are different, and that's what causes there to be a jump right here. So if we think about this in terms of limits, we can see that the limit as x approaches 3 from the left of our function f of x here is not equal to the limit as x approaches 3 from the right. And so that would mean, of course, that this limit at x equals 3 does not exist. So if the limit as x approaches a value of a function does not exist, then we're going to have a discontinuity there. And here at x equals 4, we can see that the function is defined. We have a point here for the value of the function at 4. And we can see that the right side and the left side are approaching the same value, so the limit exists. So we have both of these previous conditions met. The function's defined and the limit exists. But there's still a problem here. We don't have a continuous function at x equals 4 at this point because there's a separation here between where the limit is and the function value. So not only does the function need to be defined and the limit needs to exist, but those two things, the limit and the function value, must be the same. They must equal each other. So the full requirements for a function to be continuous at a point is that the function value and the limit are equal to each other. They both exist, have a value, and they have the same value. So a formal definition of continuity might say that the function f of x is continuous at a point x equals c if and only if the value of the function at that point c, f of c, is equal to the limit as x approaches c of the function f of x. So this contains all three requirements. The function is defined, the limit exists, and those two things are equal to each other. Okay, let's look again at each of these types of discontinuities. We have the discontinuities at x equals 1 and x equals 4. Both of these are what we would call removable discontinuities. And a discontinuity is removable if the limit exists. Next, we have this discontinuity at x equals 3, and this one we would call a jump discontinuity. And a jump discontinuity is one where the limit on the left side exists and the limit on the right side exists, but they do not equal each other. And finally, we have the discontinuity x equals 2 with the vertical asymptote where the function value is approaching infinity. So this is what we would call an infinite discontinuity. And infinite discontinuities can also be oscillating, so they look a little different. Those you don't see as often, but vertical asymptotes definitely infinite discontinuities, and that happens when the limit is as x is approaching the value from either the left or the right, or both sides, is equal to positive or negative infinity. We can also talk about a function being continuous over an interval. So if we have an interval from a to b, a function is continuous on that interval if it's continuous at every point on the interval between a and b. And then we can talk about the endpoints. So a function may or may not be continuous at the endpoints. So let's say this is the function g of x. We would say from here that g of x is continuous on the interval from a to b, but open at a and closed at b. So we're not continuous at A, but we are continuous at B. So with the case of an endpoint, it's not necessary for the limit to exist on both sides. It's enough to have the limit exist coming from the left side and that be equal to the function value, and then we can say that it's continuous at B because it's the endpoint of the interval. And at A here, the function is not continuous at A because it's undefined, or maybe it is defined but doesn't equal the limit. It would still be not continuous at that point A, so it would be open at A and closed at B.